Welcome back. This is Mr. Hassan's Maths channel, and this question is a question from the October-November 2022 International A-Level Mechanics Cambridge syllabus. It says 9709, paper 4, variant 3. And this question is question number 3 from that paper and number 10 from my end of topic worksheet on the topic of statics in my Cambridge M1 collection. And here we have a ring of mass 4 kilograms. This little ring over here is threaded on a smooth, circular, rigid wire with center C. The wire is fixed in a vertical plane, and the ring is kept at rest by a light string connected to A. Okay, if that string wasn't there, it would slide down to and probably rest at this position because it's being held vertically. So it's got its weight. It would, if the string wasn't there, it would slide to that position. The string is keeping it in this place. The highest point of the circle is A. That's the highest point of the circle. So it's directly above the center, basically. Find that the string makes an angle of 25 degrees to the vertical, and we're asked to find the tension in the string and the magnitude of the normal reaction of the wire on the ring. Okay, so that's what you have to do here for 6 marks. So let's have a look at the diagram and the forces involved here. So what forces are acting on this ring? Okay, that's what we've got to consider. Well, we got its weight. That's one thing. Its weight is acting vertically downwards. So its weight is acting vertically downward. That's one thing. So the weight of the ring, which is, its mass is 4 kilograms, so it's 4 G newtons. 40 newtons if we take G as 10, as we were going to do at Cambridge. Then you have the tension in the string, which is acting in this direction along the string, of course, and that's one of the things we have to find. We don't know what it is. And we also have the reaction force, because it's in contact with this circular kind of wire. All right. Now, what we know about the contact force, it is always perpendicular to the surfaces that are in contact. So if something's resting on a horizontal plane, the reaction force will be vertical. If it's on an inclined plane, it will be at the angle to which the plane is inclined. It will be perpendicular to the angle, perpendicular to the plane, we could say, right? Perpendicular to the plane. All right. So in this case, it's on a circle. It's on this circular wire. So perpendicular to the surface of the wire would be something like perpendicular to the tangent. So the wire at that particular point will have this kind of gradient, you could say. And what's perpendicular to that? Well, it's the line, of course, that's called the normal. And that normal line will actually pass through the center of the circle if you continue. So the line coming from the center to this point onwards, okay, the reaction force is going to act along that line because that's perpendicular to the surface. All right, so it's going to act along that line. And because the tension is acting in this direction towards the right, okay, there has to be a force balancing out acting towards the left side. So the reaction force should be such that there's a component on that side. So the reaction force should be something acting in this direction like this. So that should be your reaction force. Okay, so those are the 3 forces acting on this object. Now there are numerous ways we can answer this question. All right, I can see 2 ways which will be quite simple. One of them by resolving in the direction of one of the forces, and the other one by resolving in the direction which is perpendicular to one of the forces. That will eliminate it. That's one thing we could do. Another method is we could just, because we have 3 forces and this thing is in equilibrium, 3 forces will form a triangle, a closed triangle, which we can then use the sine rule on to find what we need. So there's 2 ways that are quite simple. But what I'm going to do first is I'm going to show you the way that most students would tackle this. It's going to be more complicated, but I'll show you that way first, just because most students would think about doing it in this way. So let me just do that first. So I'm going to think about horizontal and vertical components of forces. So I'm going to draw a line horizontally through this, okay, through the ring, and vertically through the ring, so that I can work out the angles I need. All right, so now first thing, if I want to resolve horizontally, okay, I want to resolve horizontally. I've got to know some of the angles around the T with the vertical or the horizontal so I can resolve horizontally and vertically. And same with the R. So I need to know some of the geometry of what I've got here. So if we consider this triangle that we formed when we joined the center to the end, this is the radius AC and this is the radius. These two are equal. So this is like an isosceles triangle. So this angle would be 25 degrees. Okay. And also because this is vertical and this is also vertical, because this is the line of the weight which is vertical, this is also vertical. This forms, these two angles form like a pair of alternate angles, like a Z shape. So this is also 25 degrees. So we can say the whole of this angle here is 50 degrees. All right. So that means this angle over here is also 50 degrees because they're vertically opposite, right? This angle and that angle. So I've got what I needed now to sort out solving horizontally. I can take T and I can resolve it horizontally. So I'll draw the horizontal component for T like this. And I'll have a horizontal component for R as well, which I'll draw like this. So for T, we can say that this is going to be, now if you think about the angle that we've got, this angle here with, this angle here is, let me change the color so we can see better. We've got this angle over here, that's 25 degrees. Okay, so this is going to be T times, now we're going away from the angle given. Okay, so we're going to be T times the sine of 25. T times the sine of 25. That's this component of the tension in the horizontal direction. And if I want to find the component of the reaction force in this direction, well, this is 50 degrees. This is 50 degrees. Again, we're going away from the angle, so this will be R times, and we're going to use sine of 50 degrees. That's the component of the reaction force horizontally. And we know that it's in equilibrium. So these are the only two horizontal components that we can find. So we have 2T times sine 25 must be the same as R times sine 50. Why did I write 25? That's supposed to say 50. That's supposed to say 50. Sorry about that. Okay. R times sine 50. Okay. So that's one equation that I formed from the horizontal components. If I look at the vertical components of the force, I have the tension and I want to resolve it vertically. So what I'm going to do is I'm going to draw it like this in a different color as well. Yep. I'll draw this upwards. Let me change the color. So this force resolved upwards and the reaction force has to be resolved downwards as well. So I'll draw that down here like this and just extend my page a bit. Let me just straighten out. Okay, so I have here the vertical component of the tension is going to be T times cosine 25 because it's going into the angle. And for this force R, this is going to be R times cosine 50 because it's going into the angle. It's like you're looking at the adjacent side. So if we resolve the forces vertically, the upward forces will be T times cosine 25 and the downward forces will be 4g newtons, which is the weight that's already vertically down, and the vertical component of R, which is plus R times cosine of 50. So that's equation 2. So these two equations now, to solve them simultaneously, I have to solve them simultaneously, and that's what normally happens when you have two forces and two unknowns, and resolving horizontally and vertically, we end up with two equations, and we then use simultaneous equations. Now, there's a way that I can see that will make it slightly easier for us to solve this simultaneously, and that's if I take equation 1 and divide equation 2, the t's will be eliminated directly, all right, because when I do if I do t sine 25 over t cosine 25, the t's will be eliminated. So I do the same to the other side. I have r sine 50 over 4g plus r cosine 50. So what's going to happen here, the t's cancel out, and we know that sine 25 over cosine 25 gives us the tangent of 25. They're the same angle, and we should know that from our work in P1. So tan of 25 equals r sine 50 over 4g plus r cosine 50. So now what we can do is we can multiply both sides by r 4g times r cosine 50. So we have tan 25 times 4g plus r cosine 50 equals r sine 50. And now what I'm going to do, bring the r's together. So I need to release this from here. So 4g tan 25 plus r times cosine 50 times tan 25. I'm doing this instead of writing these as decimals and then losing accuracy in my answer. Okay, and in the end I'll just put everything in it as it is. Now I want to bring r's together on one side, so I'll choose this side for the r's. So r sine 50 minus r cosine 50 times tan of 25, and that's equal to 4g tan of 25. And then I can basically take r as common. So I have r times sine 50 minus cosine 50 times tan 25 equals 4g tan 25. So therefore we can say that r is equal to 4g tan 25 divided by all of that. 4g tan 25 divided by sine 50 minus cosine 50 times tan of 25. Okay, after all that, we can now put that in our calculator. So 4g is 40, we're taking g as 10, so 40 times tan 25 divided by sine 50 minus cosine 50 times tan 25. And that gives us 40, which is the correct answer. 40 newtons. So we can say R is equal to 40 newtons. One of the advantages of keeping it in the exact form and not rounding the decimals, you get your exact answer at the end, which you're meant to get. Okay, as I said, this is a bit of a long way of doing it, right? There is a shorter way, but we haven't finished yet because you also got to find t. So we can use that first equation. We know that t sine 25 is equal to r sine 50. So we can say t is equal to r sine 50 over sine 25. And we now found what r is. So t is going to be 40 times the sine of 50 over the sine of 25. And that will give us our answer. So we have 40. So we have 40 sine 50 divided by sine 25. And that gives us 72.5046. 72.5004. What was it? 5046. So that's going to give you 72.5 newtons. 72.5. Let me write that neater. That's so T equals 72.5 newtons to 3SF. So we have our values of R and T, and that's one way of answering this question. Okay, that's perfectly fine way of doing it. But there are some ways that will take less time, and I personally think are easier. So I'm going to go through the other two ways of doing it. So let me start with the way that works. Whether the last one I'm going to show you only works if there's three forces in equilibrium. If there's more than three forces, then that method doesn't work. So I'm going to use now a method that would work even if there's more than three forces, but it makes it still slightly simpler. So what I'm going to do is I'll draw the forces again on this as we had before. So we have our weight, okay, which is 4g newtons, and then I'm going to draw there's a tension in the string, which is we're going to call T, and then if I do that, what I did before, if I draw a line, thin line, along from C, joining 4G and continue on. The reaction force is going to act along this, as we mentioned. It's perpendicular to the surface, and so it's going to be like the normal to the tangent at this point. It's going to act in this direction here. That's going to be the reaction force. And it has to be in this direction to balance out the tension, which has a component towards the right. This has to have a component towards the left to balance it out. So those are the three forces acting on this particle, right? So one of the things we could do, instead of resolving the forces horizontally and vertically, we could say, let's resolve in the direction which is, you could say, in the same direction as the tangent to the circle at the point where the ring hits it. Okay, why am I saying that? Because that's perpendicular to the reaction force, and the reaction force won't have any component in that direction, and we'll be able to work out the other forces without having to use simultaneous equations. Okay, and also let's resolve in the direction which is in the same plane as the weight. Okay, and I'll also draw another force here. Maybe, let's see, would we need that? Maybe we might need it. Let's leave it like that for now. Let's see. Okay, so I know again that this angle is 25 degrees. It's a bit too thick there. Okay, so that angle there is 25 degrees because this is an isosceles triangle. And this angle is 25 degrees because this is a Z shape, as I said, alternate angles. So these two angles together make 50. So this angle altogether here is 50. And this is the tension, that's 50. So this angle here is 50 as well. So that's one of the angles I'll need. Because I want to resolve this force in the direction of the reaction force and also perpendicular to it. And the tension, yeah, I've got this force, that's what I need here. I want to resolve it in the direction of the, yeah, so this is 50. This will also help us, this being 50. Okay, so now, let me just get rid of some of this so that I can, okay, so let's keep this angle here as 25, right? This is 25 degrees, and that's 50 degrees. That will help us with resolving the tension in the direction of the tangent and the normal. Okay, so I'm going to resolve in the direction of the tangent and the normal to the circle at the where the point is. So let's start with the tangent, which is this. Okay, so in the direction of the tangent, R has no component because it's perpendicular to the tangent. But for the tension, okay, I'm going to resolve this in this direction from here to there. Right, this has to move across from there to there, so it's going to be going away from the angle we're given. That's 25. It's going to be T times sine 25. That's the force in that direction. So I'll draw that in there so it becomes a bit clearer. Okay, so resolving this force T in this direction, okay, gives us T times going away from the angle given, T times sine of 25. So we have T sine 25, and that's equal to the component of the weight also resolved in this direction. So that's going to be in this direction, the component of the weight. And again, this is going away from the angle given, which is at 50. So it'll be 4G times sine 50. I could also call this angle 40, and it would be 4G cosine 40, which gives you the same as sine 50, but I've just kept it simple like that. So that's equal to 4G times sine of 50. Now that should give us our answer directly for T. So we have 4G sine 50 over sine of 25, and that should give us our answer. In fact, it's exactly the same sum, as you can see, that we had from the last question. This is still in the calculator. So you can see it's exactly the same. 40 times sine 50 over sine 25. So, you know, all that solving the simultaneous equations that we did in the first question, we get the answer almost immediately in this question, all right? So it's much easier to do in this method. Why? Because you're resolving in a direction in what one of the forces is perpendicular to, so it takes that out of the equation, removes some of the unknowns. If you can do that, that makes life easier. Sometimes you can't, but in this case we can. So that gives us 72.504. 72.5046 or whatever. So that's 72. Let me write that neater. 72.5 newtons. 72.5 newtons. So we found T already very quickly. Then we're going to resolve in the direction of the normal, this direction here. So what we're going to do is we can see that the T is going to be T times, and you're going into the angle. All right, so it's going to be cosine 25. And now this, the weight, you want to resolve it in that direction here. Okay, you're going to resolve the tension, the weight in this direction. So you can see in this direction, you're going to have T cosine 25 equals R. R that you have to resolve is actually in that same direction that we're resolving. But then you have to add to R the component of the weight in that direction, which is 4G times cosine of 50. All right, so we can see from here, R is going to be equal to, if we just rearrange it, T cosine 25 minus 4G cosine 50. And we already found what T is. Okay, T is 72.5046. We can use that exact value. Okay, times cosine 25 minus 40 times cosine 50. We'll use G as 10, and we get the answer. So now what I can do is, so we don't lose any accuracy, I can keep this answer. So I'll say answer times cosine 25 minus 40 times cosine 50. And that should give us the answer 40 that we had before, and it does. Good. So it gives us exactly 40 newtons. So we get the same two answers with a lot less hassle. All right, and this way works whether there's 3 forces or 4 forces. You try to resolve in the direction of one of the forces. Okay, then what's perpendicular to that will be that force won't have any effect there. So if I resolved here, I resolved in the direction of the tangent and the normal, I ended up with an equation with just one unknown, and I can use that to find the other answer for the other equation. All right, so there's one method, another method. Now the third method is even easier, but it only works when you have 3 forces and it's in equilibrium. If there's more than 3 forces, then it won't work in this way. So again, what we're going to do is we're going to draw the forces acting on this. So it's a bit of a repetition here, but hopefully it will help you. So there we have the weight, we have the tension, and again the reaction force, which is going to be acting like perpendicular to the tangent. Okay, so it's like along this line here, so the force will act in this direction. Okay, something like this. Okay, so this is the tension, this is the weight, which is 4G, and this is the reaction force. So we've got to find T and R. All right, so what we can do here is we can draw what's called a triangle of forces. Okay, and we know that this is going to be in equilibrium. So I'll draw T first. So let's say this is, we're going to draw T. So I'm going to draw a line parallel to T, just draw it a bit bigger. And then I'm going to draw 4G newtons going straight down. Now I know that there has to be another line from here where R will be, which is parallel to this line. So I'll draw a line parallel to this line and move it along here. And that line has to meet up. There have to be a closed circle. So this is T, and this is 4G, and this is R. Okay, so that doesn't mean the reaction, that doesn't mean the result, that means the reaction force. The resultant of these forces is 0. That's why they meet up over here, back to where you started again. So they form a closed triangle, and we can work out some of these angles. In fact, you'll realize something about this triangle that will make it even more make you understand something important. All right, that this is 25. And as we mentioned, this must also be 25. The angle between R and this T is 25, which means this must be isosceles. So this must be 4G, which we found R equals 40. So we can work that out almost immediately. It's an isosceles triangle, right? And then we know that this angle here is 180 minus 50, which is 130. So we can work out t using even the sine rule, right? We can use the sine rule. We can say t over sine 130 is equal to, and we can say 4g, which is 40 over sine 25. Okay, so we can say t is equal to 40 times sine 130 over the sine of 25. Okay, because just it's like 250 now, doesn't it? Sine of 25. And that should give us an answer immediately. So we have t equals 40 times the sine of 130. Okay, over sine of 25. And that gives us, as we saw before, 72.504, 72.504, so 72.5 newtons, that's T, and R, as we said, is 40. We could even use a sine rule, but we can see that they're the same. This is 40, all right? This must be 40 because it's isosceles. We could say that, R over sine 25 equals 4G over sine 25. Well, of course, they're the same. So R is 40. So we get our answers using this method of forming a triangle and using the sine rule because it's in equilibrium and there's three forces acting. Okay, if there's more than three forces acting and it's equilibrium, you won't find you form a triangle because you always end up where you start from. So if there's three forces, you'll have three lines and then you get back to where you start from. So therefore you have a triangle. So those are three ways of answering this question, okay, that I've shown you. So whichever way you find easiest, you use, okay. Other questions from this particular paper can be found in the playlist that will appear in this section at the end of the video. The link at the end of the video over here will take you to this end of topic worksheet and the topic about statics. It'll take you to the playlist for that. The link over here will take you to questions in general about statics from my Cambridge collection. And you will find that this video here will tell you how to use my channel effectively in order to find what you need, how to find my index of topics and stuff like that. It shows you how to do that. Thank you for watching and see you soon.